So welcome back. Let's move on with image transforms. And we've been through, so far, I think a lot of the mechanics of the general linear transforms. And the point I'd like to make is that all of the transforms that we're going to meet, with one exception, actually not even with that exception, but all of the transforms are going to meet within this chapter can be treated as general linear transforms. There are some that are not seen in that way, and there are some that we'll mention where either the forward or the inverse process is slightly different. But we're going to come to those subtleties in a while. What I'd like to do is to, now that, having looked at the discrete Fourier transform as one example of a general linear transform, let's now look at some others. And so the first one we're going to look at is the Hadamard transform. And this is one that is interesting to look at and unusual because it has a really nice form of generation, and its calculation is actually pretty quick as well, because it usually simply involves adding and subtracting intensities within the image according to a pattern, and remembering that an image is not just an array but actually represents a bunch of or an intensity map as a function of spatial position over a discretized space. Your addition and subtraction of pixels is just going to be dependent on a very simple spatial pattern, or a spatial pattern. I shouldn't say it's simple. So the Hadamard transform is nice because it can be represented, so going from image space, so that's again our image, into transform space, so that's going to be our transform space, is done by something similar to a separable transform in the general form of a separable transform. Indeed, it's even nicer because, and actually the first transform we looked at, which used the matrix A, it also has this property. You could also write it like this. So the Hadamard matrix itself, which is what's used in this equation here, is real, it's symmetric, and it's orthogonal. And so because it's real, it means that the conjugate or the complex conjugate transpose is simply equal to the matrix itself. The matrix is its own transpose and its own inverse. So it's really nice as a matrix. And the definition of the matrix, although there are different ways you can define it. For example, you can find definitions of the Hadamard transform that are only restricted to certain sizes of image, so only images that are an integer power of 2 in size. There are different definitions that can be used to deal with cases where the images are basically of, take average size. But have a not average size, where the images are of non-specific sizes, so just arbitrary size. That was the word I was looking for. Okay, apologies for that. So here is this is the way you define it's one definition for the Hadamard matrix. So here what we say is that the nth order Hadamard matrix is given in terms of the previous order Hadamard matrix by simply stacking the previous Hadamard matrix into a bigger array. So for example, if hn minus 1 was of size 2 by 2, so if each of these was of size 2 by 2, then this thing, when it's constructed, will be of size 4 by 4. So the definition looks like another Hadamard matrix, except or a stacked bunch of Hadamard matrices from the previous value of n, but this has a flipped sign with respect to the others. So if you want to define a Hadamard matrix, you, of course, using this equation, you have to start somewhere. And so you can start with this definition of H1. And so stacking these H1s into a bigger 4x4 matrix will give you the next order of Hadamard matrix. So that's now where is this used? It can be used in for image compression, which we'll come on to in a moment. But because it's done in such a crude fashion, just plus ones and minus ones stacked around space, it's not a very nice transform from the perspective for the quality of reconstructed images, because the reconstructed images, when you use a transform space type of compression, will always lose something, and what is lost can lead to spatial artifacts, which would certainly be present if you were to use something like a Hadamard matrix for compression. Nevertheless, it can be done, but it is also used in, so for example, in magnetic resonance imaging, when one wants to encode spatial position of an object that's being tracked during surgery, then the Hadamard type of sequence is sometimes used just to track, for example, the tip of a catheter as it moves through the body. The next transform we're going to look at is the Haar transform. So the Haar transform is based on a family of piecewise constant functions, which are known as Haar functions. So these functions represent or can be thought of as a combination of low pass and a series of band pass filters, which are not particularly smooth, but which can be represented and computed also very efficiently. Each level of the Haar transform pyramid, so when you do map an image into a Haar wavelet space, you basically get various copies of the image at different resolutions automatically computed as part of the transform. And because of that, you get spatial information across transform space, which captures different amounts of image detail, generally described as being from coarse to fine. So how do we generate the two-dimensional Haar basis functions? So the two-dimensional Haar basis functions arise from a property of separability in the one-dimensional Haar transform with respect to higher dimensions. So it's useful to look at the one-dimensional Haar basis functions first of all. So imagine that I have a signal, not an image, but a signal. Well, you can think of an image as well, but it's an image which consists of just a row of 4 pixels. So it's a really simple image, just one row of an image, and only containing 4 pixels. Then, as we've seen, the one factor that affects what the basis functions look like, or the basis images look like, is the size of the image we're going to transform. So if you've got a 4-sample signal and it's just a one-dimensional signal, not 2D, then the functions that you need to construct a Haar transform will be this first one, H naught. I'll stack it here so you can see it alongside each other, alongside the others. Okay, so if I take my 4-sample signals, so let's say I have x of n, which is my input signal, and let's say that has 4 samples. It's got x naught. Why did I write that thing there? Okay, let's scratch that. So it's got x naught. It's got x1. It's got x2, and it's got x3. Okay, so these sit in an array, which is just going to be a 4x1 array. 1x4 array. So I've made that too long now. 1, 2, 3. Okay, let's make that big. It's not meant to be big, but so we've got our samples in here, and when we apply these basis functions, what we do is we're multiplying the values in each of the basis. So this time, instead of having basis images, we have basis signals. So we apply each of these basis signals to the values x0, x1, x2, x3 in here. So let's just, that goes there. That's here. This is our array, okay? x3, x2, and that is x3. Okay, so these values sit in that array. So when we apply this thing as a basis function, h0 effectively, remember we multiply these values with corresponding values in this one-dimensional array and sum, okay, for a one-dimensional case. So what we're doing is when we do that with h0, we're just adding up the intensities in here. So remember that we talked about the little 2x2 example I gave you before, and you will see that this particular basis signal is doing something very similar. It's just adding up values, this time in a one-dimensional array. This particular basis signal here, h1 is 1 plus 1 plus 1 minus 1 minus 1. If we apply that to this signal, what we're doing is we're adding up x0 and x1 because we're multiplying and summing, and then we're subtracting the sum of x2 and x3. So a way of thinking about what's going on here is that we're adding these two intensities together, or these two values together. So adding these two values together and subtracting these two values. So what is that going to tell us? What information does the value of that result tell us? So if let's say this is now coming from an image, or one row of an image, if we get a big difference or a big value in the transform coefficient associated with the second basis signal, then that tells us that the first two values are quite different in magnitude or quite different in sign from the second two values, okay, because we're subtracting one pair of values away from the other. Okay, and an easier way to think about this is, imagine you were to average two values here and and then subtract the average of these two values here. Okay, it's kind of pretty obvious that will give you a big number if the average of this pair is different to the average of this pair. So this is just like doing that, except we're not dividing by the number of samples we're taking the average over, which is 2 samples in this case and 2 samples in this case. Okay, so think carefully about that and make sure that what I've said makes sense to you. So big values here, or big values corresponding to this basis signal, will tell us that there is a difference in intensities, if you like, between the first two values and second two values. So we're kind of finding an edge in the signal, but that edge is over a pair of values. It's not an edge over neighboring values. So that, again, we'll come to when we look at the practical on this. H2, on the other hand, is going to tell us, so first of all, it's not going to look at the last two values at all. So those two last values, x2 and x3, contribute 0 to the transform coefficient for H2, because what we're doing is, again, so if you forget about the square root of 2 for the time being, what we're doing is we're subtracting the second value, x1, from x0. That's what that's doing, okay? And in this case, that subtraction is then weighted by a factor of root 2, which is just a scaling thing for the definition of the transform. And finally, H3 doesn't look at the first two values, looks at the second two values and subtracts one from the other again. So this is telling you basically about the presence of a difference in intensity either in the first half of the 4 samples, x0, x0, x1, x2, x3. So a difference in between x0 and x1, or it's telling you about a difference that exists between x2 and x3. And that's and that hopefully will be quite intuitive to you once you think through this carefully. So what we have here are very crude forms of taking derivatives. So it's a kind of like a finite difference. These two, H2 and H3, can be recognized as basically pure finite difference operators. Again, we'll meet this in the practicals and look at the relationship between these and derivatives from calculus. But H1 is looking at derivative over a longer time scale, or a longer span of values in the input data sequence. So and that's because we're looking at the entire signal, and we're sort of considering two samples together, and then subtracting two samples later on in the signal from those. So it's kind of averaging and taking a derivative at the same time. Okay. Now, once we've got those four basis signals defined, for a 4x4, so if you now move up from a 4 sampled signal to a 4x4 little image, then you can define the 16 basis images associated with the Haar wavelet transform by taking what's called the outer product between each basis signal and every other basis signal, or between each basis signal and every basis signal, including itself. So that means you construct your basis images. So here we are using the notation we used earlier on for the simple introduction to doing two-dimensional transforms by defining this idea of the basis image. So here are the way that our basis images are defined. And here k takes values 0 to 3, and L takes values 0 to 3. And to construct each BKL, you take this outer product here. Now, what are we doing here? So here, so assuming HK is actually, I think I modified this slightly. Let's see. So that's a 1x4, so it becomes a 4x1. Okay, yeah, so using this definition here, where these basis signals are treated as row vectors, then to do what I'm doing here, when I do a transpose, then that swaps from becoming a 1x4 to being a 4x1. So this thing here is 4x1, and this thing here is 1x4. So 4x1 by 1x4 gives me a 4x4. So that's known as an outer product between vectors, which always expands. So outer products always expand your dimensions. So you go from 1 dimension to 2 dimension, or you go from 2 dimensions to 3 dimensions, etc. And so, for example, B12 would be given by this, H1, H2, and you just writing these out, you would get this. So you can see that what this is doing is it's creating a little pattern in which, if applied to a 4x4 image, the transform coefficient associated with this basis image is unaffected by anything to the right, in the right 4 columns of pixels, because they're all weighted with 0. Instead, the values to the left of the image are weighted in a sort of diagonal fashion, so that we're looking for diagonally oriented structures, preferably when we apply this basis image and compute the corresponding transform coefficient. And this is what the two-dimensional Haar basis images look like for a 4x4 image. This comes across as gray, but in this case you've got the values of all ones for the Haar basis image. So there are some definitions of Haar basis images where there's an extra scale factor here. I haven't used a scale factor in this definition. So in principle, these are not orthonormal basis signals, and these are not orthonormal basis images, but they are orthogonal, and to make them orthonormal, you simply need to include an extra scale factor, which you can find in some of the lecture notes. So now the Haar, again, so these are the basis images for the Haar, two-dimensional Haar wavelet transform, but you can also calculate these by a separable transform, in which case if you simply stack the basis signals into a 4x4 array like this, a 4x4 matrix, then that represents H4. You can use that to transform an image using a separable calculation from image space into transform space. Okay. Now, so far we've looked at at a series of transforms in which the basis images or signals are predefined and are unrelated to the data apart from the size of the input image. So we choose a basis set we want to use or transform type, and we then define the basis images according purely from the nature of that, the nature of the transform definition, and the size of the image. There are transforms that are instead defined by the data or by the images. And so one example of those in image processing is known as the KL transform. And it's awfully similar to principal components analysis. But in the case of working with images, it tends to be known as the KL transform. So the KL transform is defined in terms of the covariance structure of a collection of images. So you need to have a set of image examples in order to compute a KL transform, and then to be able to find the basis images associated with the KL transform. So this is a collection of images. So this is image dependent. Okay. So the way that the basis images of the KL transform are defined is by stacking the images up into an experimental space, like we talked about in chapter 1, and then removing the mean, finding then the covariance, the covariance matrix. In fact, it's covariance it's a four-dimensional kind of covariance function, but you turn that into a covariance function which is kind of deals in flattened images. So what you first do is you take an image, you unravel it into a long vector, and let's say that vector is 256 in length because you've started with a 16 by 16 image. That 256 length vector then represents each pixel in the image. And what you're then doing in looking at a covariance structure is you create a covariance matrix, which will then be 256 rows, so one for every pixel in that image, and 256 columns, also one column for every pixel in the image. And that covariance structure the covariance matrix is big. You then find the eigenvalues and eigenvectors of that covariance matrix, and you sort the eigenvalues and then find the corresponding eigenvectors and align those with each of their eigenvalues. When you've got those eigenvectors, you can take the top, let's say 100 or 200 or 50 eigenvectors, and wrap those back into images. So you will have, so let's say we do 50 eigenvectors. The top 50 eigenvectors, or the eigenvectors corresponding to the top 50 eigenvalues of that big 256 by 256 covariance matrix. And those top 50 eigenvectors you wrap back into images, and you call those images eigenimages, which kind of makes sense. Those eigenimages can then be used to project your whatever images you want to represent against. So to transform images using the KL transform based on that collection of image data, you then take an image, whether it's from that data set or not. As long as it's the same size, you can then run through the process of taking the matrix inner product between your image to be transformed and each of those 50 eigenimages, and so you get a 50 value transform space, and that's the encoding of your image. That's the transform domain of your input image. So here is that process of just doing just describing the reminding you what the eigenvectors of a matrix are. So they're the vectors x such that CF times x is equal to lambda I by x. And so you get, and the lambda i's here are the eigenvalues of the matrix C, or covariance matrix C for the image. So if you have big images, then because you need to create a covariance matrix that has that's the number of pixels squared, which is what this implies here, it can get computationally pretty hairy to do that. But the other problem you can have is that the although images that have been used to in the generation of a covariance structure will probably be encoded very nicely, there's no guarantee that images from outside that data set will be encoded well. So there is, just to show you a couple of examples of things. Oh, I think I can use the same. So here in the notes, you can see an example in which I've just taken 4 example images. It's just a line that's kind of, at different orientations in space. And these are the eigenimages, first 3 eigenimages from the covariance matrix of that very simple set of 4 example images. So the eigenimages kind of capture the basic structure, but have signs that are negative, positive, and 0. And these are the approximations of these examples from the original data set using these eigenimages. So to construct these 1, 2, 3, 4, I'm only using the top 3 eigenimages, which are these, even though I have many more eigenimages in principle within the or defined by the covariance matrix of this set of images. And that's because, so again, if these are examples where the size of each image is 16 by 16, and so the point here is that this is exactly the case in which we would have a 256 by 256 covariance matrix, which you can imagine is finding the eigenvalues and eigenvectors of that takes a bit of computational effort. Okay, so oh yes, I was also going to show you some these other examples here. So this is from a collection of images known as CFAR, a CFAR 10 data set. So each image is either 32 by 32 or 28 by 28 pixels. So it's quite small. And these are the principal eigenvectors. I think it's the first 100 eigenvectors obtained from the stack of the images in the CFAR data set. And down here, what we've got are approximations to these images by using the projections of the original images here against these basis images shown here. And I think I've used the first 100. So it's an approximate reconstruction from around 100 images. So it's not perfect, and in some cases you can see the images are quite blurred. But as you add in more of the eigenimages, you will, which makes the approximation better, you will eventually get to a point where you can't tell the difference between these images, which are reconstructed from the eigenimage projections, and the original images. You won't be able to tell the difference. Okay? Right. So we now come on to the question of what does it all mean? So we talked in kind of abstract terms. So we have these images that we know are two-dimensional functions which are spatially varying. And we know that these linear image transforms provide an alternative representation which allows us to go from image space into transform space and back again. So instead of describing our image as a function of space, we can effectively describe an image in transform space. So what do we want our transform space to give us in terms of properties? If we were designing one and we wanted to have a wish list of properties for transform space which have some advantages over the representation of the image in image space. So first of all, we don't want to spend a lot of time doing our transform. And secondly, we want to be able to make sure that if I define an image transform, I can very easily convey that definition to someone else so they can define the same transform. It's a bit like cryptography, where you want to share a key so that you can exchange messages. So you want to have a simple transform definition, and there are lots of predefined image transforms out there already. So it's very unlikely you would need to define a custom transform yourself. Usually something that's already been defined will, sort of do the trick for you. You also want to have a fast transform computation, because you don't want to spend a lot of CPU cycles or time or energy computing forward and inverse transforms. So on that topic, it's also nice to be able to have an exact and a fast transform inverse. Now, these two things are not necessarily equivalent. So you can have some transform inverses which are not exact. They're only approximate. They can't be made exact. And so the forward transform is applied, but after the forward transform, there's no guarantee you can get back exactly to the original image from transform space. However, if you can get back, go into image space and get back, you would want to have both a forward and inverse process be fast, so you don't spend a lot of energy. And the last two properties are actually they're sort of optional, and they depend on the context of use. So sometimes you want the image transform to provide a compact representation of the image. So for example, if you are doing image compression, then something known as the energy compaction property of the image transform is very important. In other cases, you don't really care about having a compact representation in transform space. You prefer to have something like the transform space allows you to find features more easily, like lines or edges. And so sometimes you trade off something like a compact representation for easy working with, so that it's easy to find image features in transform space. So now it's worth having a look at that, and a little demo of that. Right, so let's drop into our web thingy. Good, there we are. Right, so here is an example of that last point, this point about being able to find features easily in transform space. So this is what I'm going to show you is an example of a transform. It's not usually considered as a linear image transform, but you can make it a linear image transform. You can define basis images for it and so on. So I just realized that this is partly out of scope. Let's get that into properly into scope. Okay, I think this is showing up, but right, yes, okay, so good. So I'm probably chopped off here, but I can bring myself in. There we go. Okay, so let's have a look now at this thing, this little demo. So the radon transform, it's widely used in, well, it was used quite a lot in something called in X-ray CT, in the early days of X-ray CT, where it gave mechanisms of reconstructing. It's used as the basis for reconstructing images from projections through a patient of X-ray photons. So we're going to look at something that's it's known as a straight line Hough transform, which is related to the radon transform, because basically the straight line Hough transform usually refers to a mechanism of finding lines within an image, whereas the radon transform is used in medical imaging, but the two are very closely related. So I'm going to sort of use the term interchangeably, but strictly speaking, to get a straight line Hough transform, what you do is you first apply edge detection to create a binary image where the large, or you find boundaries using, sort of thresholding, and then sort of finding the boundary pixels. And then you apply the radon transform on that, which then gets you into what's called a Hopf transform space. So let's see how this works, because it's really cool. I think it's cool. So let's say you got an image which contains a bunch of pixels that are forming a line in image space, but crucially these pixels are not all, there's gaps between them. So, and that happens when you do something like edge detection, and then you get imperfect edge detection, and so you want to find where let's say the lines defining a corridor are, so that a robot can then navigate down it, or find where a doorway is so the robot can navigate through it. Very common sort of thing in robot vision. But sometimes the lines that you get when you do edge detection will be broken. So you want to be able to find the presence of pixels that are in a linear, that are geometrically aligned into lines in different directions and sort of positioned at different places in the image. But you may have gaps between the pixels. And that's where something like the radon transform comes in handy, or the straight line Hopf transform. So here's a little example image. And so what the radon transform does, and I'm going to illustrate this with in a slightly messy way. Let me see, is this going to work? No, it's not going to work as an illustration, but imagine that, oh, I know, let me just jump to open board. That's the solution here. So let me show you how the radon transform works very quickly. So we jump to our board scene, and we jump to a nice fresh page. So the way that the transform works is, here is our image array, and so we have our lines. Which define our pixels. It's a really shockingly distorted grid, but let's roll with it. And let's get rid of this stray thing here. Okay, so what we do now with our to define our straight line Hopf transform, or to compute our radon transform, is you draw imaginary lines through this grid, and you start off, let's say, so it's a bit like linear projections we looked at in chapter 2 earlier in this chapter, right? So basically you draw imaginary lines through here, and along these lines you compute the sum of intensity values. Okay, so along each of these you do a sum. Okay, so you're just basically computing sums as a function of position along this direction here, right? Effectively along this axis, and then and you keep on doing that through the whole image. Then what you do is you change axis, and to make the drawing easier, let's do an axis going like this. And you then repeat the process of drawing straight lines through here, and along those straight lines, and here you need to figure out how to draw lines diagonally and at different angles, but you just need to do something called interpolation to do that. We'll talk about that in chapter 4. So you basically draw lines along a different angle, and again you compute the sum of intensities along these lines. Okay, so sum. Okay, so that's what you do. And what you also do is to define the coordinate system that you use for the lines at different angles. You make a funny looking coordinate system that looks like this. This is typically the coordinate system that's used, but it's not the only one that's possible. So this is the angle of the line you're drawing, like this. Okay, so that's a right angle there. And this here defines theta that is used kind of almost conventionally for how to draw these lines. And then that distance from here to here is called rho. So basically, as I draw different lines along like this, I am changing my value of rho. And as I move through different angles of lines, I'm changing my value of theta. So in the end, when I do these sums, I can put the sums into an array that has on one axis has theta, and on the other axis I have rho. And so this is called my Hough transform space. You can also call it a radon transform space as well, but in image processing, computer vision, it's known as the Hough transform space. Okay, so that's this space here, which has rho on one axis and theta on the other axis. Okay, so now given that we've done that, and I've done that in this in this little Jupyter demo, then what we end up with, let me just expand this. Oh, oops. Why did I tilt myself there? Yeah, okay, I think am I getting everything in here in this? Yeah, I think I am. Good. Okay, so if we now go back to our web page, scroll down here. So here, for example, is this is our theta axis, this is our rho axis. So this is called the offset, and that's called the angle, as you would expect, right? And you can see that what happens here is that we get a peak. Well, we get a bright region, let's say. You can't see it's a peak very easily in this, but you get a brightest region there, which corresponds to an angle of around 45 degrees, and the rho value, the position along this axis, is telling you where you are, where this line is. This line here is of pixels in image space. So if I move this line, kept it parallel to itself and moved it over here, or moved it up here, then it would shift around in this direction. That peak would shift around in this direction in image space. And if I change the angle of the line, it shifts around in this, the peak shifts around this direction. So to see it's a peak, you can do a little surface plot of it. And there you can see it's not just a peak, it's a really sharp peak. And so it's very sensitive. This technique is very sensitive for detecting straight lines. Now, if you have two lines in the image, then you get two peaks in radon space or Hough transform space. So, and it therefore becomes really easy to use this technique to be able to detect the presence of lines in an image, because these peaks will not change if, for example, you put bigger gaps between the lines, and you had between these points on the line, and if you had interfering points that weren't parts of lines, those will become kind of they will also form hypothetical bumps in. So I call them hypothetical bumps because they kind of, each bump can be treated as a hypothesis, or each peak can be treated as about a hypothesis about a line's presence in the input image. But unless you have lots of reinforcement of the things really all lining up nicely, then those bumps will be lower in amplitude than the real lines. So it's a really nifty way for detecting lines in images, straight lines in images. Okay, so let's come back now to the notes. So that's why we would use this, this easy to find image features. So sometimes we design a transform not for doing only for doing feature detection, and actually we don't necessarily care about going back into image space. So some transforms don't need to be invertible if you want to use the transform to do feature detection. Okay, so the biggest application by far of image transforms is in image compression. So you use that energy compaction property we mentioned before. So here's a little demonstration of that, where you take an image of a knee, and then you can reconstruct it using a fraction of samples in transform space. So here you can immediately see it looks like an image of a knee, but this uses a fraction of the values in transform space than that present in image space. So won't talk more about that here. You can read a bit more about that in the notes. From the perspective of image compression using transform, sometimes the KL transform, although it requires that you do this you have this learning process, so it's an example of what's called a data-driven transform. And the KL transform optimally, statistically decorrelates images according to a linear measure of correlation. The KL transform is considered to be kind of a gold standard for image compression. However, it's only going to be as good as the collection of images that has been used to define the basis images of the transform. If the images you actually want to compress fall outside of that example set, then your compression may not be as great as you'd like. So there are other ways of finding or constructing let's say data-driven basis images. So the independent components analysis gives you another way of doing this. ICA is interesting because its forward transform is not that simple to compute. Its inverse transform is just like that of other basis images we've looked at, where you basically take the transform coefficient, multiply it by the basis images, and sum everything together, so a blending of the basis images. But going from image space into ICA space is quite complex and needs an iterative algorithm. So we've talked about compression. Other applications of transforms are image enhancement. So for example, here we are doing Fourier domain image enhancement. So here you've got an original image. Here I've added noise. It's not white noise. It's actually spatially correlated noise that's been added on top of the image. And you can see that the level of noise is quite high and the degree of spatial correlation is quite strong, so that it kind of really masks the image pretty well. But nevertheless, from this, you can reconstruct that, a cleanish version of the original image, by taking this image plus noise into transform space and then applying a masking function, which is called a filter. In this case, it's called a Butterworth filter. So it's a two-dimensional analog of a one-dimensional Butterworth filter, which you probably have met previously in biomedical signal processing or in signal processing itself. And so by applying that as a multiplier to the Fourier domain representation of this and keeping just things that fall within the bright region of this circle and gently masking out everything that goes beyond this region with a falling Butterworth characteristic, and then reconstructing from discrete Fourier space back into image space, you get this result. And so you can see that the house is quite visible. So this is a nifty thing, and it relies on the fact that here the noise is added to every pixel and distributed all the way through space, image space, whereas in Fourier space, the structures of the house, the spatial structures of the house tend to occupy the smaller region of the inner region of Fourier space. The noise, on the other hand, despite being spatially correlated, occupies a much greater range of Fourier space than the image information. And so the spatial information, the house information is concentrated in Fourier space, and the noise information is more distributed across Fourier space. So that if I preserve just stuff that's in the center of Fourier space, where this information is, then I am increasing the proportion of signal information in the reconstructed image compared to the image plus noise in the spatial domain. So that's why this works. And so it relies on a very precise relationship between the the basis images, the structures that you want to preserve in the data, and their relation to those basis images, and finally the structure of the noise and its relation to the basis images. And so if your basis images are able to capture stuff from the image domain in a select part of transform space, then you can use this trick to suppress coefficients in transform space that are outside the signal region but possibly lie in the noise region, and then invert out of transform space. So that's a general technique that can be used provided that you've got the right relationship between signal, noise, and basis images. So I talked about feature extraction already, which gave you the example from the radon transform or the straight line Hough transform. Here's another example of using a wavelet transform, and what this is doing when mapped into transform space, which is shown in 3 separate components of transform space here. So all of this is part of transform space, and in fact there's a lot more. So this particular transform space is very overcomplete. So there's more transform coefficients than there are pixels in the original image. So you wouldn't use this for compression, or at least it's not natural to use this for compression. But you can use this transform space very nicely to find edges of boundaries, and also to determine the direction in which the edges are running. And you do that by comparing the outputs from coefficients across transform space that basically have different orientation selectivity. So again, it depends on the relationship between, well, it depends on the structures you have in your basis images. Okay, so I've given you that example already, and that brings us to the end of this chapter. So in this chapter, we've looked at a number of linear image transforms with most emphasis on 2D discrete Fourier transform. We've shown that the 2D DFT is one of a large number of possible linear image transforms, and all of these can be represented as a matrix inner product between an image and a set of basis images, and we've looked at examples of what those basis images look like. We've discussed the computational cost of computing image transforms, the importance of separable image transforms. We introduced the Haar transform, and we also talked about the applications of image transforms. So that's it for this chapter. In the next chapter, we're going to look at, so these transforms basically look at the entire space of the image. You may have a bit of localization going on in the transforms. So for example, if you look at so these transforms, so this transform space, for example, is localizing, it preserves where the big values of transform coefficients are, which are either so gray is 0, light is, so bright is positive, black is negative. And so we have big values in transform space corresponding to where we have edges in this particular part of transform space. But one of the things we will see is that very often, as in the case of the Haar basis images, you actually want to, like the Haar basis images, you actually want to focus on information that's happening in a local neighborhood. So rather than looking at structure that's across the whole image, which something like this transform will do, but in a rather complicated way, you want to focus in on structure, local spatial structure, or neighborhood spatial structure. And that's the role of neighborhood spatial operators in image processing. And so we're going to be looking at those in the next chapter.